now. So Sam is going to continue with effect handlers.
Yeah.
Yeah. Thank you.
I'm slightly tempted to just wait in case. Oh no one else is coming. Yeah, okay. So I'm gonna move on to my next set of slides on effect handler oriented programming. I'm actually gonna go over some of what we saw yesterday. So if you didn't get all of that, then it might help a second time. If you have any questions, then do slow me down and ask. Mostly today, I'm going to just show you lots of examples. But I'm going to just start with this slide. Right. Revisiting, there's a whole load of effect handler oriented programming languages you might like to look at. I guess these were sort of in two groups. These ones are very researchy. All of these ones are maybe, like OCaml, for instance, existed beforehand and had effect handlers added to it. In fact, that's probably true of all of these. Unison is a sort of intriguing language. It's not specifically built around effect handlers, but they added effect handlers based on Frank. And it's not developed by academics. It's a more sort of industrially oriented language with a focus on distribution. And I had this list of resources which I'm showing again. But let's get back to where we were. Oh, yes, this picture as well. This view of effect handlers as composable user-defined operating systems. Although now when I first showed you that, I hadn't actually said what a handler is. Now you can maybe map that onto some of what you saw before. So conceptually, we have this stack of features that are being built up, each one providing different effects, and then they can propagate down, perform their own effects that might get handled later and ultimately reflected in the outside world. Oh, yes, and I wanted to say this. That was kind of the view of effect handlers as little operating systems. Another way of flipping that idea on its head is, we can use effect handlers to build operating system-like functionality, which I think are very suited to. This EIO library is quite an impressive library built in OCaml for doing it. It gives a wrapper around some very high performance, low level IO functionality. I can't remember the names of the message passing systems it builds on. And that's being used to build, amongst other things, the Mirage operating system, which is implemented in OCaml, and it's a unikernel operating system. So you dispense with most of everything except what you need for your particular application. That's the idea when you build an application against Mirage OS. And this, I think, is really fun. Daniel's work from his PhD thesis, where he really composes together lots and lots of handlers in order to build a version of Unix. I mean, a kind of toy version of Unix, but it's a really nice illustration of what you can do with effect handlers. Okay. So now, I'm going back to starting with some of the examples I showed you yesterday. The difference today is I'm going to write a type signature on each of my functions so you can see the effect typing that's going on. So, why don't I just work through this again? So just to remind you, I maybe didn't spell that out. This is a call by value setting, which means that when you have a function type, On the left-hand side, you have a value type. In the case of toss, it's just the unit type. It doesn't take anything. And then on the right-hand side of the arrow, we're going to have two things. Or another way of viewing this is this is a function that takes unit, and it's going to return a toss, which is either heads or tails. That's the value it returns. And then this thing here is the effects that might be performed when we run the function. So sometimes another way of writing this, you'd have seen that in Wen Hao's talk yesterday, is kind of you write the effects on the arrow, because conceptually they're the things that can happen when you run this function. And this is saying, well, it has the choose effect, which itself, when you perform it, takes unit and gives you back a Boolean. And then I've written E there to indicate, well, there may be other effects as well. Why? Yep.
The exclamation point is special means for the part of the thing.
It's punctuation,
Okay.
just like the arrow.
Or just separate.
Just separating the value type from the effects.
Okay.
Yeah. So yeah, you might wonder, well, why have I bothered writing this E thing here? Now, supposing I want to use toss in some other context. Well, in fact, we see this right down. Oh, well, if I could have replaced, you should probably notice that this expression here is exactly toss. So if I'd written toss there, for instance, in this context, we have two operations happening. We have choose and fail. So by saying, well, there's some other effects as well, we can then instantiate this E to include those effects. And in a language with type inference, that's done by unification. So yeah, these things might actually turn into type variables or effect variables. Because yeah, I mean, it's sound if I use toss in any context which is happy to perform the choose effect, but other effects as well. Okay, and then yeah, the drunk toss, if you remember, was representing the drunk trying to toss the coin, and there's as well as the choose effect, there's the fail effect, because they might drop the coin. Yeah, this was a bit subtle, but the idea here is, well, fail is an effect that takes unit and can return any type at all, or it doesn't actually return any type at all. Because we know it's not actually going to return, it's okay to say that. So it's the standard thing with exceptions. If you have an exception, you can raise that exception whenever any type of value is expected at all, because it's an exception. Does that, any questions about that? Is that clear? Good. And then yes, we first make a choice to see whether the drunk catches the coin. If they don't, then we fail. If they do, then we decide whether it's heads or tails. And we can just use these functions like any other function. So this is just a recursive function that's going to toss, or try and do a drunk toss n times, counting down each time you recursively call the function. Clear? Yeah. And I showed these different kinds of handlers. Again, yeah, another bit of syntax I bring in here, which is, this is the type of a handler. It takes a computation type to a computation type, and a computation type is a value paired with some effects. So this particular handler is handling fail, and we've written the E here again to say, well, oh, there could be other effects here, and what happens to those? They're going to just bubble up through this handler to be handled by some other handler. And we're going to handle an A computation by returning a maybe A. And the effects after we've handled fail are going to be just the remaining ones, because we've handled all of the fails. And this was a special case of a handler where we don't actually use the resumption, well, because we can't, because there's no way, I can't, there's no function that will generate an arbitrary A for any type. Yeah.
Does that mean that if, oh, thanks. So you're saying that the effects that stay after, because we assume this maybe fail handles all the fails, that it would not type check if we pass it to something that would handle fail?
That's a very good question. You mean if we want to handle all the fails and then we want, you might try to instantiate E with something that has fail in it as well. Yeah, that's a bit subtle. Am I even going to get to that? I might get to that in the third lecture. But yeah, you have to be a bit careful about that, because... No, actually, I'll get to that at the end of this lecture. But for now, let's just ignore that possibility and just assume that E is other effects. Because yeah, you have choices about this, like whether, well, what does this... I sort of deliberately picked this syntax, suggestive of disjoint union, to imply that these E's cannot include fails. But you can have choices there. You can allow multiple instances of the same effect, for instance. Sorry? That's also a possibility. So, for instance, the Frank programming language does exactly that and does allow you to choose. Coca also does something like this, whereas other languages like Lynx do not. Instead, you kind of have to say, yeah, you end up being polymorphic in whether fail is... You'd have a different type over here to say, well, fail may or may not be here. We don't know. But we're not talking about polymorphism yet, so let's not worry. Yeah, and this behaves as we'd expect if we just have a... Yeah.
Effect handler can change the type of computation.
That's what an effect handler kind of is for, in a sense. I take a computation of, well, in general, some computation type C and turn it into a computation of type D. It interprets some of the effects and the other ones propagate through to be then subsequently handled by another one. And then you plug all these little interpreters of effects together, and ultimately you might get a pure program at the end, or you might get one that performs some side effects that are handled by the outside world. We can't implement, I don't know, fire a nuclear missile as an effect handler. That has to be a... Or, yeah, I mean, or we can't implement just printing to the screen as an effect handler. We can plug into the built-in facility of printing to the screen, or... Anyway, I'll show some examples of that later as well. And then this was my first, a handler for choose, and a silly example. It's not silly, but it may well not be what you would want your implementation of choose to do, because it always chooses true. But here's where you get the resumption, remember, and this represents the rest of the program after the choose. So if you did, yeah, I must admit the examples I'm giving here are a bit simplistic because I'm only doing a toss. So let's go back to, I'll just show you what that definition was. No, okay, I guess it's all right. When you do the choose, well, what is the rest of the program in that or the bit of the computation you're handling, the rest of toss? It is if something, then heads, else tails. So we just substitute that with true, is all that happens in that case. So we just get heads, as you see. This one is more interesting because it's doing the same thing. We get this resumption. But we can see in the type here, we're returning a list of A's rather than just a single A. Because we're returning a list, that also means the return case has to do a singleton list. But this resumption for the rest of the program, the thing that does if something then heads or tails, we run it twice, once with true and once with false, which is why we get, if we handle toss, we get heads and tails. Yeah.
I don't know if this question even makes sense, but are effects blocking coupled?
Yes.
Yeah.
This is
What you want?
no, not necessarily. You could build maybe more interesting semantics, but that's more complicated. So yeah, I mean, there's this, the semantics or the vanilla semantics of effects and handlers is completely deterministic. I mean, the way I'm interpreting your question is, you could imagine, well, when I perform one of these effects, I might be running other things in parallel, and yeah. I mean, they do integrate smoothly with parallelism. It's one of the nice things about them. They tend to integrate pretty well with any built-in effects you have. And in OCaml in particular, they did this whole multi-core OCaml work, and there were two aspects to that. One was the concurrency aspect, which they did with effect handlers, and the other was parallelism. And they combine nicely. You can define your effectful computations and implement them with parallelism underneath. For instance, you can implement work-stealing schedulers, where you actually send these resumptions to another processor. Okay, and I have another question. Yeah.
Continuation. When is that something?
Well, maybe it's best for me to show you the operational semantics, and we'll see that, and I'll go through that more slowly. But no, I'll answer your question first, just by looking at this. So actually, yeah, because I haven't. Nothing happens at all. If I just try to run one of those programs without installing a handler, then it just blocks. It gets stuck, or I get the equivalent of an unhandled exception error, an unhandled effect error. In order to run it, I need to install a handler. This example, sorry, I did have examples here. That's what these things are doing. Yes. So actually, no, I could have. Sorry about that. I could just use the examples here to illustrate this. So if we take the simple true choice one, when we do handle toss with true choice, what does that do? That installs a handler which delimits the execution of this piece of code, whatever code we write here. And that now means that any choose operation that gets performed inside this piece of code will search for a handler. And that is the point at which the resumption gets constructed. So in this case, we just run as normal until, right away, we encounter the choose operation. And this toss is in the scope of that handler. At that point, the program searches for the handler. It finds it immediately because it's the immediate thing. And then it captures the rest of the code in the context of that handler. And the rest of the code in that context of that handler, remember the code was just toss, is exactly if something then heads else tails. So that's exactly what the resumption is in that case. modulo, it's a bit more complicated. It's actually not just that. It's a function. It's a function that takes a value, and then it does if x, then heads, else, tails. And in fact, the whole body itself gets wrapped in the handler as well, because if we happen to do some more choices here and here, then we want them to get handled. So that's easier to see here. In this case, the continuation of this choose is going to be if x, then if choose, then heads, else, tails, else, fail. And you want to make sure that when you run that thing, this choose and this fail also have the opportunity to be handled by the same thing. You had a question, Dean.
I was going to ask, like, if the assumption was basically taking the argument and replacing it.
Yes. Yeah. No. We spell that out with the operational semantics, so maybe. Well, we'll get onto that. I guess this example. There's something more complicated going on because we've got two handlers. And right, when we do the drunk tosses, well, what does drunk tosses do again? It's going to just run as normal. I mean, if you don't encounter any operations, you just run your code as normal. So drunk toss is going to run this thing, and then the first thing it's going to do is a choose. But the handler we have here is maybe fail, which doesn't handle choose, which means that actually it's going to bubble all the way out to this handler. And your resumption ends up being extended so that it includes, it will be handle, and then however far we got with drunk tosses with maybe fail will be all included in that resumption. It's somewhat hard, I guess, to get your head around exactly how that works, but it does. And I showed you this example before, and it turns out it gives you something meaningful. And yeah, the point is, whenever you come across a choose in this computation, it's going to bubble out to this handler, the one that does all choices, and whenever you come across a fail, it won't. It will get handled straight away. And yeah, if you just look at the types, you see that you get a list of maybe tosses when you compose these things together. I'm not sure it's worth dwelling on this though, because you have to sort of stare at it and play around with it yourself to really understand the mechanisms. Yeah. Yeah, that's a typo, isn't it? You're right. Yeah, it should be list of maybe, list of toss. But it does end up doing the right thing in that this corresponds to catching the first toss and it being a head. This line corresponds to catching the first toss and it being a tails, and then this is when that first toss gets dropped. And then these are the cases where the second toss gets dropped. Yeah.
I forgot what this return thing does. If you go back to the handlers.
Yeah. Return says what you do. If you imagine it, we're handling one of these computations. At some point, it finishes and it just returns a value. That's what programs do, or functional programs do at least. And that just says, well, what do you do when you've finished with that value? And very often, it's just the identity. It just says, oh, well, you get an X, return an X. If the type here and here is the same in A and in A. But in this case, for instance, because we want to return a list of A's, if we get a value back, we need to make sure we return a singleton list. Similarly, with the exception handler, when we were interpreting A as maybe A, we turned X into just of X. Okay. Yeah, and there is this point that if you compose, did I get the types of that right? That's probably also a list of maybe of list of toss, but the result is nothing anyway. So because this one, as soon as if it encounters a fail anywhere in its execution, which it does, then it gives up. Yeah.
First example, list of maybe, list of toss. So
maybe list of
the
toss.
inner list comes from the.
So we just compose the two handlers together. We have, if we take handle drunk tosses with maybe fail, what does maybe fail do? So what does drunk tosses do first? It returns a list of tosses. Maybe fail, that's going to take the list of tosses and it's going to turn that into a maybe list of tosses.
Oh, okay.
And then we're applying all choices, so it's going to turn that into a list of maybe list of tosses.
So the inner list comes just from the type of drunk tosses, and then the outer list is the non-determinism.
Yeah, and quite clearly, if you compose the things the other way around, you get a different type, which it's only natural. That's the way types should work. I guess I couldn't show you that yesterday because I hadn't written the types in. No.
Something he said no.
I want to show the operational semantics. I don't want to show the
Could I just
denotational.
glimpse the denotational semantics so I can photograph it and then obsess over it later at my own time?
I'll do it offline.
Sure.
Afterwards.
Okay, thank you.
And the slides will all be made available anyway afterwards. All the slides will be. So you can. There's a version of them available. There will be a version here as well. Right. Okay. Yeah. I'll show you. I can't remember exactly. All right. Yeah, we get onto the operational semantics after this. Although I could show you. Well, this is a simpler example. So maybe I'll show you this one, and then I'll go over the operational semantics again. Right. What's the point of this example? So this is actually more in the scope of the kind of application I envisage handlers being used for now. A form of concurrency, we could say, implementing of generators. So our effects, we're going to have just a send effect. So it's yield style generators. You can think of send as being like yield. You have this in languages like Python and JavaScript, where you write a function and it starts executing, and at some point it will return a value, but then you can call the function again and it will keep on executing and return a different value. People, who's familiar with generators? Almost everyone. Okay. So here's an example of a generator. So it's going to just send. Well, if you run this naively forever, it's going to just give you a sequence of natural numbers, ever-increasing natural numbers, by invoking the send operation, and then recursing and incrementing. And again, we have the effect here. We see that it can perform send, and it can be used in the context of other effects too. And so in order to give meaning to this, we have to write a handler that says, well, what does a send do? So this is basically code that would consume the generator. So what's this example going to do? It's going to we pass in a number at which we want to stop, and it's just going to keep on consuming the generated natural numbers until we reach this. In fact, until the number we get is greater than or equal to stop. And here we see the type of the handler. So actually what I'm writing for the types of, this is an example of a parameterized handler. Parameterized handlers, as well as taking a computation type to a computation type, they're also allowed to take some parameter that gets threaded through as well, which, in fact, this didn't, does this even need to be, it probably doesn't need to be done as a parameterized handler, but yeah, anyway, it is. But yeah, this is going to return the list of natural numbers. So again, in the return case, well, we need to get a list out. And the computation we're handling has unit type, so we know that the value we get back there is unit. We just return the empty list. And then the interesting case is where we get the send, and we have the resumption. And if we haven't, if n is less than stop, then we just output n in our list and invoke the resumption. Now, normally when we invoke a resumption, well, you give it the type, the return type of the operation, unit, and that's this bit here. But with parameterized handlers, you also get to update this parameter. So the reason I said, well, this doesn't actually need to be a parameterized handler is that actually stop doesn't change. But this would allow us to update some sort of state each time you handle the operation. And then, yeah, if you reach stop, you stop doing this. I guess if we didn't have something like this, then you'd just end up, well, it would never terminate. You'd be generating an infinite list. But an example, if we try to handle nats of 0 with until 8, then sure enough, we get the list 0 up to 7. So, question?
Let's see how the comparison match up there. In the lower branch, or in the lower case, where you handle the type, you do have something effectful. Yeah. Is the continuation effectful or not? Does it have the send effect in it?
It does.
Okay, so
no, hold on. It doesn't.
Right, because it implicitly gets wrapped with
the handler around the body of that continuation.
All right. So in both cases the return type is the list without the
return
send
type.
effect.
The R is the list. Yes.
Right.
And we'll see that on the. I'll show you the typing rules.
And hence the parameterized handlers, because the implicit wrapping has to happen, so you can't just use recursion if you...
Well, yeah, yes, no, absolutely. There's another class of handlers we'll get onto, which are called shallow handlers, which do not do any wrapping at all, and then you can just use recursion in the way you said. And they're actually, in a lot of ways, more convenient to use, but less semantically well behaved and harder to optimize potentially. But okay, so operational semantics. Now we'll see quite a lot of what we were talking about actually in action. I've shaded the bits that distinguish this as being parameterized handler. So, did I? Yeah, right. Hang on a minute, did I do that? Right, yeah. So when we did this handling, we gave it not just the handler, but the initial parameter as well. Yeah.
I notice we're not treating non-termination here as an effect. If I'd done that nats 8 until 0, is there a reason to keep the example small? Is there something that
it
fundamental
works
limitation?
absolutely fine if you have non-termination built into your language. On the other hand, let's see. If you don't have non-termination in your language, then you can't write an example that doesn't terminate. Moreover, although in this rule we see there is actually some recursion, because we have handle with H here and we have handle with H here, and you might think, well, can I implement non-termination using this? You can't, because this is a form of a fold or a primitive recursion. Something is always getting smaller every time you do that. The thing that has got smaller is we started off with an evaluation context that has an operation in it, and over here that operation has disappeared. And, well, okay, the argument for why it terminates is a bit complicated, but let's not get distracted by that. Anyway, yeah, going through this again, I think this bit is probably entirely straightforward. Right, the H here. So the handler is parameterized, and the idea is that this H could appear in all of these bodies of all of these clauses. So if we handle, this is the final return value. If we just have a value here, then we fire off this case, we bind V to X and W to H. Any questions about that? I hope that bit is. Jamie?
So is it recorded? Sure. Yeah. Okay. I just wanted to check. It looks like it's waiting for someone to press the record button. Sorry for the interruption.
Okay. And this is the one that does all the clever stuff. This is when we actually encounter an operation. So you're in an evaluation context, and an evaluation context in this simplified setting is basically just a whole load of nested lets inside a whole load of handlers. So you can think of this as a sort of a stack corresponding to where you're currently evaluating. But it's the stack as far as the handler that is actually going to handle the operation. This side condition is kind of important here. This is saying that the operation isn't handled by any other handlers that happen to be in this evaluation context. So this is the nearest enclosing handler that actually matches op. And I guess it's probably unsurprising that you take, if we come across an op, then we take the body of whichever clause matches that op. We take the value that's passed in and we substitute that for the parameter for the operation. We also take the parameter for the handler and substitute that in for H. And we need to generate this resumption, and that's, well, yeah, I guess that's the most important part. And the resumption is a lambda, which is going to allow us to update H to a new parameter, also take the value that we want to substitute into our evaluation context, and it just continues evaluating the evaluation context, but after rewrapping the handler around it, the same handler with the new parameter. And this is what distinguishes a deep handler from a shallow handler. The fact that we do this rewrapping here, and this is the thing that means that if we come across any other instances of op, then they're handled in the same way. So, any questions about this? Yeah.
So the side condition. So E contains all the handlers which are kind of above the current one, or like outside the current scope of the current one.
No. E will contain all the handlers that don't handle op. So for instance, in the example we had before, where we had an inner handler, the fail handler, but we performed a choose, it will contain maybe fail, because that does not handle choose, but the H we have here will be the thing that does handle the choose.
So it contains the inner handlers, like, yeah.
It contains all of the ones that
didn't handle
that we've bubbled past.
Yeah.
Exactly. So you extend the resumption as far as it needs to go, up to the point at which the matching handler is found, and because then that means that, well, when we resume, it also contains lets, you see. So this thing, we might have let x equal choose in do some more stuff, and the do some more stuff, that might need to be handled by one of those inner handlers, which is why we need to capture them as well. Right. Yeah.
Thanks. I'm a bit confused by the second two cases. What the n is? So I can see the n in the let reduction rule, but what's the n in the handle with cases?
Oh, I'm assuming that all these rules are defined with respect to h of h.
Oh, okay.
So the n, this n is this n here, and the n op is, well, one of these op ones to op k's. I could have written it differently, but this was just a reasonably concise way of expressing this. Oh, right, yeah. An exercise you could try is you can. If you don't have parameterized handlers, you can encode them using deep handlers by basically, the idea would be to create a handler that returns a function, and then you can simulate this passing of parameters. But it's kind of convenient to have them built in like this. Yeah. So yeah, I have loads more stuff I was potentially planning to cover today, but I think that's fine. We can just slow things down, and I'll get to it tomorrow. But yeah, now showing you the effect type system, the typing rules. We've seen all of this illustrated. A computation type returns a value and an effect, separated by this bang, which is punctuation, as I said. And effects are just collections of operations. The rule for operations just says, well, if I want to perform op, then it must be in my effect type. I mean, in a sense, yeah, effect type, it's really a sort of context, an effect context. It tells you which operations you're allowed to perform. Yeah, and obviously the value you have here must match up with the input type of the operation, and the thing you get back is the output type. And handlers are really in a sense, they're just a form of, they're kind of like a form of application, where you apply the handler to a computation. Well, you apply it to the initial input value for the state. That's this P here, and then you also apply it to a computation which you handle any operations of. It's not that dissimilar from a normal application rule for functions. And then this is the rule that does all the heavy lifting. So what is one of these parameterized handlers? Well, I've written a lambda here to indicate this is the initial parameter we get in. So h is bound inside n and the ni's, and we can see that here. It's in the context, and it has the parameter type. You have the return clause, which binds a value x of type A. Now, what was A? A is the initial return type of your computation you're handling. And you see that all of these clauses must return a computation type D, which is the thing that comes out at the end. Now, what else happens? Oh, for each operation clause, P has type AI, which is the input type for the operation. And the resumption is going to take the new parameter and the return value for the operation. And it also gives you back this final return type D. Now, the fact that you're seeing all these D's here is the thing that tells us that we must be applying the handler to the body of the resumption as well, because that's the only way we know of turning a computation of this type into one of this type. Any questions on this? Yeah.
So the lambda for the parameter, that's supposed to be a different kind of lambda than the normal lambda, right?
Sort of syntax. I mean, when I wrote the examples, I wrote it as a named function. Yes, it's a sort of, it's again part of the punctuation, you could say, and different actual realizations in different languages do this in different ways.
I imagine in a practical language there's no difference in notation between parameters and arguments.
And normal arguments. Yeah, typically not. Although the initialization, there's sometimes some weird syntactic sugar for that. But any further questions on this slide? No. Okay, this is another example we've seen before. Cooperative concurrency. So where we have threads that can yield control, and yield doesn't take any payload. It just says, oh, I want to yield control. I realize I'm not that keen on this presentation of this example, because the shallow handler version is much simpler, but let's do it anyway. I showed you this yesterday, but this time we have effect types. And it gets a little bit complicated because, in fact, we need recursive types here, as we will see. So we're going to have a type of threads. Threads, again, I'm just going to assume they don't actually take any input values or return any values, but they can perform the yield effect. But But the resumptions, it turns out, that we're going to be generating are not quite the same thing as threads. Remember, in the parameterized case, you take a parameter and then the continuation, then the result returned by the operation. So this is basically the resumptions we're going to get whenever we perform a yield. And what's the parameter going to be here? Well, it's going to be a list of resumptions. So this is where the recursive type is. And then, well, the one arrow, one bang E is that the one is the one that comes from the return value of the yield, and then this is going to be the computation type that we're handling is going to return unit as well. So the parameterized handler we're going to define is going to take a collection of resumptions and return a unit. No, sorry, and then handle a computation of unit type that may perform yields and consume all these yields, so they all get handled somehow. And actually, yeah, this code I'm reasonably happy with. It's just these things are annoying because they're recursive. They're not the things we actually want to pass in. The thing we'd actually want to pass in would be these things, threads. So we need a way of turning these things into those things. But if you look at this code, I think it basically just very directly does what you might imagine a scheduler to do. This list of resumptions, it's kind of the queue of threads that are waiting to run. Well, if the current one that we're currently running finishes, then well, we just take the next one and pass in the rest of the list and unit. But if we come across a yield, this R prime is the resumption of the current thread. We again run the next one, and we add the current one to that list. And then if there are no other ones, then you just keep on running the current one because there's nothing else to switch to. And yeah, the slightly fiddly bit is that, well, the thing we actually want to write is this cooperate function, which takes a list of threads, like the things I showed you on this here, and then runs them through the handler. So that's what this co-op with is doing. It takes a thread and turns it into a resumption. And well, how do you do that? So here we are really relying on having some recursion, because co-op with itself is going to use co-op. But you do more or less just follow your nose to work out what to do here. You do the only thing that you could. We want to generate something that's going to take a list of resumptions, and then produce a thunk, a thread. And what's that thread going to do? Well, we want to handle that thread with an appropriate handler. Well, and what handler do we have? We have co-op, which we pass in then the R's that we got there. And then having done that, if we get a list of threads, well, we can do co-op with on a thread that just immediately finishes, which will fire off this clause and then carry on with everything else. And we've mapped this coercion over all of those threads. And then, having done that, it nicely it does what we expect. I'm wondering how much more I can... Oh, I can at least show you the shallow version, because that is nicer. And then we'll stop. So shallow handlers have a slightly different operational semantics and typing rules, but the difference is exactly that you do not wrap the handler around the body of the resumption. So what that means is that each time you invoke the resumption, if you want to handle it in the same way, you have to reinstall the same handler. I'm writing a little dagger to indicate that this is a shallow handler rather than a deep one. But here, in this case, we don't need to worry about the parameterization with parameterized handlers, because we can just make use of that recursion to thread parameters through functions in the normal way. And we end up with a situation where the type of threads is the same as the type of the resumptions we're going to get. So in particular, note that the yield effect is still present in the resumption, in the body of the resumption. But this is nice because we can just pass in a list of threads. And in the case that it's empty, well, you just stop. But otherwise, you've just got these two cases. If we yield, well, we just stick the thread on the end of our queue. And if we finish, we just carry on with the rest of the threads. And that's it. And it behaves the same way. Which I think is nice. Oh no, I do have that, yeah. I'll flash this up. Key here is you see the handle doesn't appear there anymore. We just continue the evaluation context. A disadvantage here is that you really need some form of recursion here, otherwise you can't do anything interesting at all. And you see again in the types, what's the key change? It's that the resumption does not return a D because it's not handling the thing. It returns the original input computation. So we're out of time, so I think we should stop.
Last questions? No? Okay, thanks, Lindley.